flux change problem where you don't have an obvious circuit. I'm going to do a demonstration here. I have a big magnet, real strong magnet, and I have a copper plate here. And this is soft copper. It's a very, very good conductor, big, heavy plate. This magnet has a north pole on the bottom. I'm going to drop it towards the plate, okay? Watch what it does. Is that? I love that. I never get tired of this. Check it out. Oh, got a little, I'm going to make no ting. Here we go. Oh, yeah. Can you see it bounce? Here's what happens. The magnet's falling towards the plate, and it's making a huge magnetic field that goes downward, right? And so I'm putting a downward flux into the plate. And the plate is made out of copper. It's a really good conductor. And there's not a loop of wire, but shoot, I can make a loop anywhere in this wire that I want to, in this plate that I want to, right? I could draw an infinite number of loops inside here. The whole thing's a conductor. So what happens is I get a huge change in flux inside the copper, and it's going to generate currents which flow around inside the copper. Huge change in flux downward. There's going to be a huge current inside here. And what direction flux will the copper try to make? Upward. Oh, and think about this. If there's a downward flux here, there's a north pole on the bottom. This thing's making a flux upward. Where's the north pole? On the top or the bottom? Top. Where the magnetic field comes out of. I got north pole versus north pole. What happens? Repulsive force. And the repulsive force keeps them from just slamming into each other. Here's the really crazy thing. If I take this thing and flip it over so that it's upside down, I get a flip side to that. And I'm going to need someone to hold this copper plate for me. And Ryan, are you volunteering? Excellent. So I need you to kind of like hold this up. Go ahead and hold it up off the wood. And if you could come around this side, yeah, so we'll be able to see this. Go and hold up just the copper, about like 6 or 8 inches off of there. And I'm going to take this magnet and put it up underneath like this. And I'm going to let go. And it doesn't immediately fall. Why? Now the north pole is going up inside here, so I'm making a flux up inside it. But now it goes away, and the copper tries to replace the flux. It doesn't fall immediately. So the copper makes an upward flux to try to replace the flux that went away. And so this is the north pole on the top, on the bottom, south pole, because the field lines are going into it. And so the force is not repulsive this time, it's attractive as it goes towards it. And actually, Ryan, if you take that down and lift it up quickly, the magnet will come with it. Put it right down on it, and then see if you can quickly, oh yeah. And it doesn't want to move away from the plate. Thank you very much for your help with that. Let's have a hand for that. Feat of strength here in front of the class. So then, too, it'll slide down the plate. Check this out. If I tip it up like this, because it's moving on to a different part of the plate, and so it makes this changing flux, induces these things called eddy currents. So you don't need to have a circuit in order to have a flux change, in order to have this whole Lenz's law thing go on. And let's look at another example that works like that. If you're trying to like stimulate someone's brain, you're trying to stimulate neurons, you have to do that by putting in an electrical current. Oh, here's the problem, though. Your brain, though a very good conductor, is wrapped in an insulating wrapper. Your skull, not a very good conductor. So trying to electrically stimulate someone's brain is hard, except magnetic fields will penetrate insulators. So if you put a coil of wire on top of someone's head and really switch on a huge current in a very short period of time, what it will do is generate a huge magnetic field, penetrates a person's head, I get a changing flux, and I get these so-called eddy currents that go inside someone's brain. Okay? And this is a really useful therapeutic technique. It's being used potentially to treat depression. But it's a really interesting research tool, because you can stimulate one part of someone's brain repeatedly, and you can fatigue it. And basically, you can like turn it off, because you can make a part of someone's brain so tired that they aren't able to use it. So you can like go in and like really like work the thing that allows you, the part of your brain that allows you to like generate speech. Then you show the person a picture of a cat and say, "What is this?" And they go, and they can't answer. Seriously, it's really quite remarkable. And then it comes back. It comes back. You're just fatiguing it. It's like if someone asked you to like lift a weight 100 times, and then someone asked you to like lift a carton of milk. You can't do it. But tomorrow, the next day, you can. This comes back. It's kind of a, but it's a really interesting thing. And they use it to test what like broad areas of the brain are for. Fascinating, fascinating thing. I'm going to do a calculation with it. And this is a calculation. And it uses a picture that I got off the internet. And I'd rather suspect that this is not a real picture of someone having this technique done. I rather suspect it's not, because this is like a huge coil of wire here. It was making a gigantic magnetic field near this coil of wire because there's a huge current inside it. And look what the person's wearing. Rings. Oh, if I have a huge magnetic field that suddenly shows up, I get a huge flux change inside the rings that's going to induce EMFs that's going to make currents flow inside the rings. And let's just do a quick calculation for this. So this is a typical machine. The field near the coil will go from 0 teslas to 2.5 teslas in a time of 200 microseconds. Technician holds his hand near the device with the increasing field direction along the axis of his hand, so the flux goes through his 2-centimeter diameter gold wedding band. Question, what EMF is induced inside the ring? Okay, let's take a look at that. Here's how you calculate it. First off, we have a relationship that tells us the EMF that's induced inside a loop due to a flux change. And it looks like this. Delta V is equal to the number of turns times delta phi divided by delta T. Okay, what's the number of turns? It's a ring. 1 turn. So this is just 1. Okay. Delta phi, phi is flux. That's a product of the magnetic field times the area. Does the area of the ring change? So we can simplify it to this. It's the area times the change in the magnetic field divided by the time required for that change to happen. Oh, and what's the change in the magnetic field? It goes from 0 to 2.5 teslas. So what's the change? 2.5 teslas. How much time does that take? 200 microseconds. So delta T, 0 is 200 times 10 to the minus 6 seconds. Then we have the area. And it's a wedding ring. It's a circle. So what formula do you use to compute the area? Pi r squared. So this is pi r squared. What is the radius? 1 centimeter. The diameter is 2 centimeters, so it's pi times 0.01 squared. I have everything I need in that expression, and I calculate a voltage of 3.9 volts in this case. Okay? And you're saying to yourself, well, that doesn't sound like such a big voltage. And here's the thing. It isn't such a large voltage. But it's a voltage inside a gold ring. Metals are really good conductors. And gold is like the best conductor of all. If you could afford it, you'd have gold wires in your house, okay? Because it's a really good conductor. It's a really good conductor. As a matter of fact, I worked out what is the resistance of my wedding ring all the way around. 0.5 milliohms. How much current? If I have 3.9 volts across a resistance of 0.5 milliohms, I, delta V divided by R, 3.9 divided by 0.0005, 7,900 amps. 7,800, sorry. You won't get 7,800 amps because the whole point of the current is to oppose the change in flux. And it will oppose the change in flux. But you will get a large current, and you'll get a current that's probably hundreds of amps. And if you have a current of hundreds of amps that's flowing through a conductor, what is it apt to do? Heat it up. It's going to get real toasty. And here's when I had an MRI taken of my shoulder earlier in the year. I asked them if I could keep my wedding ring on. Because what I wanted to do was get inside that big solenoid, and you're in there for a long time, and there's all this banging going on. What are you going to do to amuse yourself? Here's what you're going to do. You take your hand, and you put it like this. So the axis of the magnetic field is through the ring. Oh, and then as I change the magnetic field, I could feel it vibrate. Because if they change the magnetic field, it's a changing flux, which makes a current in the ring. And the current is going to feel force from the magnetic field. Sweet. Yes. And so I could feel this. My ring is like dancing around. And the other thing, too, is it got really, really warm. How can I make it stop? Turn it like this. And if I turn it like this, there's no more flux through the ring. So I was like doing this, like feeling my ring like go and get toasty, and then like nothing. And I was kind of like doing that. It was pretty fun. They just told me I had to keep my hand away from like the operational like stuff that they were doing over here, like whatever, just because the magnetic field that you'd make would kind of like potentially upset things. Very, very cool.